Now let's take a look at setting up a version of the glass fracture manually so that we can control and art direct this precisely how we want to. So I'm just going to do a 1-point scatter for an impact point on the surface. And on that scatter, I'll set the force total count to 1. I'll turn up the point size so you can see it a bit better. And let's template our glass pane and change our global seed until the point is in a position that we want it to be. I'll just go with this fairly central point here. Now we're going to start with the circular cutters, so I'm just going to use a copy and transform SOP to duplicate that impact point. So if we want 10 circular cutter rings, I'll set the copy total number to 10. So now if you middle mouse that, you can see we have 10 points just stacked on top of each other. And then we can randomize the scale for each of those. So drop in an attribute randomize. We'll set the attribute name to scale. The distribution will be a custom ramp. And we'll turn on both fit value 0 and fit value 1. So we'll try a minimum size of 0.2 to start and a maximum of 2 units. And we'll connect the copy to that, and then add a copy stamp to add tubes to each of those points. So we'll attach the points to the second input and a tube to the first. And then change that tube direction to face in the correct axis for our glass pane. In this case, we want to face this on the Z axis. And right now it's randomizing the scale on all 3 axes. So I'm just going to add a wrangle after that scale randomize. And then in that point wrangle, I'll set the scale Y to be the same as the scale X, and we'll set the scale Z to just a value of 1. Now the nice thing about setting this up this way is that we can use the custom ramp on the scale randomize to control the distribution in ring sizes. So if you want more of those circular cutters to be closer to the center, you can grab the midpoint of this custom ramp and drag it down so that more of this distribution area is concentrated on those lower values. Now with this default interpolation type set to monotone cubic, it might be a little bit too flat on the low end there, so you might want to change that interpolation to linear. And I'm going to do that for all 3 of these points. Although you can certainly feel free to experiment with the other interpolation types if you would like. And if you don't like the specific distribution that you're getting, you can go to the Options tab and change the global seed value to find a different distribution that you like more. So I'm liking this distribution here, although maybe I'll just turn down the minimum width on this fit value 0 a little bit. I'll change that down to 0.1, and I'll bump up that fit value 1 to 2.5. Now ultimately, we're going to want these circular cutters to be polygons instead of just a tube primitive. And if you go to this tube and switch that primitive type to polygon, you can see that's looking too low resolution, especially on the wider rings. And we don't want to turn up the resolution globally on the tube because the smaller rings don't need nearly as much resolution as the wider ones do. So on this wrangle just before we copy those tubes over, I'm going to set a resolution attribute that we can then stamp onto the tube. I'll rename that to tube attributes. So in this bit of Vex, we're adding a divisions attribute and doing a fit on the scale X size so that when that scale is 0, we're getting 10 divisions, and if that scale is up to 5, then we get 100 divisions. And then to stamp that onto our geometry, you can go to this copy stamp here, go to the stamp tab, turn on stamp inputs, and for attribute stamps, we'll type in divisions because that's what I called that attribute that we set up in the wrangle. And then on the tube, go to this columns parameter, and we're going to stamp in that value that we set on the attribute. So we'll point that stamp expression to our copy circular cuts, we'll look up the divisions attribute, and set a default value of 5. Maybe I'll turn up the rows as well while I'm at it. We'll we'll set that to a value of 4 so that our circular cuts aren't perfectly straight through the surface. And these divisions actually look like a decent starting point, although if you need to tweak that, we can go back to our tube attributes wrangle. Maybe I'll up the larger division size to 150 divisions. Now we can add a little bit of noise to this, since we typically wouldn't want our circular rings to be perfectly smooth circles. And to set up that noise, I think I'll solid template our glass pane and then drop in a mountain sop. And when you're working on glass fractures, a lot of people make the mistake of making their cuts far too noisy and jagged. If you look at glass fracture reference, you'll see that a lot of these cuts are actually fairly smooth, and a lot of those jagged features that you see are really a product of fairly smooth cuts all combining together in interesting ways to create all of those interesting sharp shards. Of course, there is some jagged detail in there, and different types of glass may shatter in slightly more jagged ways than others. Like you can see, this type of glass is certainly much more jagged than that regular plate glass. And for glass like this, I would typically do a Boolean fracture to define those large shards, and then do a Voronoi fracture pass on top of that to get all of these little cellular cracks in there. So it's really important to check different references for the types of glass that you're working on. For the building and the shot that we're focusing on for this class, I'm treating the glass like fairly standard plate glass, so these shards are going to be fairly smooth in shape, although we're not going to see those glass shards super close up, so we're not going to need to be super picky about those shapes. And although we don't see the glass super close up in the shot that we're working on, it's important to get used to these types of fractures because seeing these really up close glass fractures are quite common in production. So on the mountain sop, a height of 0.79 and element size of 1.76 looks like a decent starting point, although I think we still need to go even higher with the divisions on our tubes. And after increasing that, we can move on to creating the radial cracks coming out from that center impact point. I'll rename our main impact scatter to impact point for clarity. And to create those radial cracks, it's essentially going to be the same process. I'll copy the num circular, and instead we'll create a num radial. And for these radial cuts, we're going to copy some grids instead of tubes onto these points. So I'll just drop in a grid. And instead of a stamp for this one, I'll just use a regular copy to points. We'll pipe that num radial into the second input of that and the grids into the first. And then we'll randomize the normals to get some rotations on these. So I'll create a randomize for the n, set the attribute name to n, and then the min and max will be -1 and 1 for both x and y, and then for z, that'll be 0 for both the min and the max. Now we really just want this to rotate around one axis, and if you display the points, let's template our glass pane again, and then turn on the point normals, you can see all of our point normals are pointing in the correct directions. Those aren't actually unit length normals, so if you want to, you could normalize those with this checkbox on the attribute randomize. But even though these are just rotating around one axis, we're still getting our grids all over the place. And we can fix this by setting an up vector on our points. So I'll use an attribute wrangle, and in the wrangle, we'll set a vector called up equal to 0, 1, 0. So straight up and y. And once we set that up vector, you can see the rotations of all of these grids are now matching the normals that we set on those points there. And then we can go in and modify our grids. It looks like a size of 0.5 and 15 is sufficient to cut all the way through this glass pane. And I'll set this to 200 rows and only 2 columns. Or we could go a little bit higher than 2 if we don't want that to be a perfectly straight cut through the glass. So I'll try a value of 4. Now if we add some mountain noise to this, you can see a couple problems here. One of the problems is that parallel cutters are getting essentially the same noise shapes, and it's possible that's a desired feature, but generally I would try to avoid that. And the other problem is that our grids no longer converge to a point at the middle. Now to address the matching noise shapes first, let's create a for each connected piece loop, and we'll connect our copied points to that. And if you display the begin, you'll see it's just processing one of our cutters at a time. Now let's put our mountain inside that for each loop, and then display that, and we're going to add an expression to the offset. Now we have this unique class value for each one of these cutters, so I'm going to add an offset in Z. I'll say 100 times the primitive class value. So we'll use a prim function to look up from input 0, and we want prim number 0 and the class attribute. And because this is just an integer, not a vector, we can enter 0 for the final bit of that expression. Now this offset is still just a value of 0 because we're operating on the piece with class equals 0. You can verify that by checking the spreadsheet, and sure enough, that's class equals 0. So let's go to the for each end and turn on single pass and pick a different cutter number. You might need to hit this reset cached pass option. And now, if you go back to this mountain SOP, you should see a difference if you get rid of that offset versus having that offset in there. And then when you turn off that single pass option, you can see that we no longer have those matching noise shapes, and each piece is getting some unique noise values. Now to make all of these cutters converge back to that exact impact point, we're going to use a distance fall off to control that noise. So to make this a bit easier, I'm going to add a rest position SOP just before this connectivity loop, so that we have our rest position stored before adding that noise. And then after the loop, I'm going to add in a point wrangle, and we'll connect our cutters to that. And in the second input of the wrangle, we'll connect our points that we are using to scatter those grids. Now adding this bit of vex will give us some distance fall off to that noise that's being added to those cutters. It starts by getting the distance from the current cutter point to the point into the second input of that wrangle. That's our central point there. And then it remaps that distance with a fit function so that at a distance of 0.2, we get a value of 0. At a distance of 5, it's a value of 1. And that gives us a blend value that we can then use to lerp between the rest position and the noised position. That lerp is just a linear interpolation, just a fancy way of saying blending or mixing between those two values. In this case, the current point position and that rest data we've stored before applying the noise. So if you want to change the fall off on that noise, you can just change this fit function that's remapping the distance for this blend value. So if you change that from 5 to 2, then it's going to bring that noise in closer to that impact point. So now we have our concentric circles, and we have our radial cuts, and we can merge these together. Maybe I'll change the height of our concentric rings to match our radial cutters a little bit better. So I'll turn that height down to 0.5. And this is looking like a decent starting point for our glass pattern, but we want to have some more random cuts across the surface as well. Now for these extra random cuts, we don't want to base that on this impact point at the center. We're going to do a new scatter directly onto our entire glass pane. So drop in that scatter, connect it to the glass pane, and I'll set the force total count to 10 and display that. I'll also turn off the relax iterations, which I think is pretty important for this because you can see that relax is just pushing those points all the way to the outer edges of the glass pane, and we want this to be a bit more genuinely random. And then to copy the actual cutters onto these points, I'm just going to copy this section that we used to copy those grids to that center impact point. We'll copy this randomize n and the up vector and the grid itself. And then we'll paste this over here for our new scatter and connect the scatter to that. So now we have these extra cuts scattered, and in this case we'll still run into that problem where parallel cutters are going to get some pretty similar noise shapes. It's not super obvious here, but you can start to see some of those parallel areas lining up too much. So I'm just going to copy the same connectivity loop that we used before to vary up that mountain noise, and we'll paste that over here. And as an optional step, I'm going to go into the mountain here, and instead of a 100 multiplier, I'll change that to 150. So now we have unique noise being applied to each of those cutters, and we can now merge that in with our concentric rings and our radial cuts. And then we're ready to apply the Boolean fracture. However, before we actually run the fracture, I'm just going to do a little bit of extra attribute cleanup, because any attributes on our cutters will be copied over to our fracture geometry, and we might not want that. So in this case, I'm going to remove the rest position and the up and the class. And I'll also add some normals since these cutters currently don't have any. Now, since we're only cutting this one pane of glass, I'm not going to bother using the shatter HDA. I'll just use this Boolean fracture SOP directly, and we can connect our glass pane to that and our cutters to the second input. On the Boolean settings, we'll set treat as to surface. And since I don't expect to refracture this any further, I'm going to leave detriangulate turned on. I'll turn off this exterior group because we don't need that info, set the name prefix to glass underscore, and we'll use an exploded view to check our results. Now this is looking like a nice first pass at the glass fracture. At this point, I would compare to some reference images to dial in the noise settings and number of cutters to get everything looking just right. In this case, I'd say maybe there are a few too many of these circular rings right in the middle there. And for some of these extra cuts that cut across near the middle, it can be nice to manually or procedurally bulge those out so that instead of cutting through here, they kind of cut a shape a bit more like this and kind of line up with those circular cutters that you have in there. In the past, I've used a bulge deformer for that sort of thing. But there are always lots of different ways that you can procedurally modify your geometry. Now to finish up our glass fracture, let's do some final cleanup and pack our geometry. And it looks like we have some disconnected points that we'll need to clean up, and it looks like we're missing the inside faces as well. So for the inside faces, let's try flipping this Boolean fracture from treat as surface to a treat as solid instead. And this isn't necessarily the most straightforward option because with a regular Boolean shatter, we're used to using solid for the first selection and surface for the second. So typically A is solid, B is surface, but in the case of the Boolean fracture, we only have the one option. So it's understandable if you find that to not be very obvious or straightforward which this is referring to. With many tools in Houdini, if you're ever unsure about what exactly it's doing, you can always feel free to dive inside and investigate. And inside this Boolean fracture SOP, you can find a regular Boolean SOP in here. And if you allow editing of contents, you can see what these parameters on the underlying Boolean are linked to. So in this case, it looks like the B input is defaulting to surface, whereas the A input is controlled by this parameter on that Boolean fracture. So with those inside faces fixed, we can do that extra bit of cleanup for those disconnected points. So on the clean SOP, make sure to uncheck remove degenerate polygons and leave that remove unused points option turned on. And you can see those extra points go away. And now let's do a pack based on the name attribute. connect the clean to our pack, turn on the name attribute option, and we'll select the name attribute to be transferred to our packed geometry. And finally, we'll create a null at the very end to refer to this elsewhere in the scene, and I'm just going to call this out glass fracture. And now that our glass fracture is complete, we can use these shapes for our shattered window simulation for our full building.